Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we are discussing the speed control of a series motor. We will continue from that. Now, we have seen the speed control by voltage control and resistance control. Today, we will see the speed control by field control. Now, this is the field control. We have the speed torque characteristic. So, by speed control, by using field control, we mean we are actually changing the field constant, that is Kf. So, Kf appears in two terms, the first term and in the second term. Now, if we plot the speed torque characteristic, speed is in the y axis and torque is in the x axis. So, let us say this is the speed torque characteristic for some value of Kf, let us say Kf 1. Now, when we decrease this Kf, what happens that the no load speed increases and the negative term also increases. So, the speed torque characteristic will change in the following fashion. This is for Kf 2. So, we further reduce the value of Kf. So, in that case the no load speed will increase and the negative term will further increase. So, this is Kf 3. So, Kf 3 is less than Kf 1 is less than Kf 2 and is less than Kf 1. So, when we go on decreasing the value of Kf. So, this is Kf is decreasing, Kf decreasing, the speed torque characteristic changes like this. Now, if we have a load torque which is a constant load torque, so when we have a constant load torque, the intersection of the load torque with the load torque profile with the motor torque speed characteristic decide the operating point. So, we have for the first one we have the speed is omega m 1. For the second characteristic of the motor, the speed is omega m 2, and for the third one the speed is omega m 3. So, it means the speed increases. So, it means if we go for field control, which means we are reducing the field constant, that is Kf, the speed increases. So, the field control is employed for higher speed application. Employed for higher speed application. Now, we have seen the characteristic of a shunt or separately excited motor and also that of a series motor. Now, let us try to summarize the behavior of shunt motor and series motor in the following lectures. Now, we will be first taking off motoring and electric braking of shunt or separately excited DC motor. So, we have discussed about the motoring part. Now, we will be taking up motoring once again and in addition we will be focusing on various types of electric braking of shunt or separately excited DC motor. Now, we will be comparing the motoring with various types of brakings. Let us see what are the various types of brakings we have along with the motoring operation. Now, we say that this is motoring and we have regenerative braking. We have a braking called dynamic braking. We also have a braking which is called plugging. We will discuss about the various braking method along with the motoring of DC motor. Now, let us take up a DC motor here. We have the field and we have the armature and this is applied with a voltage that is V. So, the armature is carrying a current that is I A, the armature resistance is R, the back EMF here is E. Now, in motoring the current enters the motor and there is a conversion from electrical energy into mechanical energy. So, we write down the equation in the armature circuit here. So, the equation in this case V is equal to E the back EMF plus I A into R, and from this we get I A is equal to V minus E by R, which is positive. Now, if we simplify this, we also write down here E is equal to V minus I A into R, and from this equation we have already seen that omega m is equal to V by k phi minus T r by k phi square. So, this is the characteristic of separately excited DC motor. Now, in this case for motoring operation, especially for motoring operation of DC motor, the applied voltage should be higher than the back EMF. So, the condition is this, that the applied voltage should be higher than the back EMF for motoring and the current is positive, the torque is also positive and of course, the speed has to be also positive for motoring. Now, let us come to braking. What do we mean by braking of the motor? When we talk about braking, we are bringing down the speed. So, the motor speed is brought down to 0 or maybe reduced to a low value, that is the meaning of braking. So, when we are braking, the motor is sometimes functioning as a generator and it is delivering power back to the supply or back to some resistance. So, in regenerative braking, the motor is functioning as generator and it is supplying power back to the DC source. So, here we have the similar circuit here for braking, in this case regenerative braking. We have the armature and we have applied voltage V, the field and the armature, and this is the armature current I A, the resistance, and we have the back EMF, that is E. Now, in this case also we can write down the Kirchhoff's voltage law, that is V is equal to E plus I A R. And what about I A here? I A is equal to minus of E minus V by R, and this quantity is negative. So, for regenerative braking the current is negative. Now, we write down the back EMF expression from this equation, the first equation. E is equal to V minus IAR, exactly same as the motoring. So, from this we can find out the expression for the speed. Omega m is V by k phi minus T r by k phi square. Now, we see that the equation for motoring and regenerative braking are the same, but the operating zones are different. For motoring the current is positive, for regenerative braking the current is negative, the armature current is negative. So, that is one of the difference. So, here the voltage, the applied voltage is less than the back EMF E. So, this is our back EMF. So, the applied voltage is less than the back EMF, and the current here is negative. So, it means the current is being fed to the applied voltage. So, the current direction is opposite here. So, it means the motor is working as a generator, is driving power to the DC source. And then what about the torque here? Torque is negative here, and speed in this case could be positive or negative, but these are our equations. V is less than E, I is less than 0, I is negative, and T is less than 0. So, the motor is behaving as a generator. Now, in dynamic braking what happens that we excite the field from a DC source, but the armature is disconnected, and the armature feeds a resistance. The armature feeds the current to a resistance. Now, this is the armature current I A, the back EMF is E. Now, we can write down the equation here. Here we do not have any applied voltage, this is the resistance here. So, the applied voltage has been short circuited. So, when we have a dynamic braking, the supply is removed from the armature, and the armature is thrown to a resistance, that is effective resistance is R. Now, here 0 is equal to applied voltage is 0 is E plus IAR. Now, what is IA? IA is minus E by R. So, current is negative. So, as before the current is negative here, it means the current here is flowing in the opposite direction. So, it is circulating through the resistance. So, it is being dissipated as heat in the resistance. Now, if we write down the expression for the back EMF, E is equal to minus IAR, that is now applied voltage, V is equal to 0 for the armature, or omega m is equal to minus T r by k phi square. So, in this case the torque is negative and the current is also negative. So, this is the dynamic braking where the energy of the motor is dissipated in the resistive part of the armature as heat. Now, let us come to the fourth method of braking, that is called plugging. So, in plugging what happens? The field, but what we do here, we reverse the armature connection while keeping the field connection as it is. So, we reverse the armature connection, we have some armature resistance here, the armature connection is reversed while we keep the field connection as it is. Okay. Now, this is the back EMF of the machine, that is E, and the resistance here is R. So, if we write down the Kirchhoff's voltage law for this circuit for the armature, so voltage V is equal to minus E, and then we have some drop here, this is IA, the armature current. So, V is equal to minus E minus IAR. So, what is IA? IA is minus V plus E by R. So, we have to understand that in plugging we reverse the armature voltage. So, the resistance has to be sufficiently high. So, this has to be sufficiently high value, this has to be sufficiently high. So, when we go for plugging, the armature resistance has to be sufficiently high to limit the current through the armature, otherwise there will be over current. Now, if we see the equation for the back EMF, the back EMF is equal to minus V minus IAR, or from this omega m is equal to minus V by K phi minus T R by K phi whole square. Now, this is the equation for plugging. Now, in this case the current here has to be negative, the current flows in the opposite direction like this. This is the voltage, and the applied voltage is being held by the back EMF, current is flowing in the opposite direction, current is negative, and the torque is also negative. So, these are the conditions for plugging. Now, we have seen motoring, we have seen regenerative braking, we have seen dynamic braking, we have seen plugging. Now, if we want to appreciate the behavior of the machine in a speed torque plane, we have to plot the speed torque characteristic for all different conditions for motoring as well as for braking. Now, let us see the speed torque characteristic of a separately excited DC motor under all possible conditions. This is the speed axis and we have the torque axis here. Now, usually for motoring we have this behavior, and if we increase the resistance, change like this. But if we extend this to the second quadrant, this characteristic will be like this. Similarly, this is for a different resistance. If we increase the resistance still further, get it like this. Similarly, if we go for reverse motoring, we have the profile like this, and if we increase the resistance, if we further increase the resistance, so this is, let us say, the no load speed in the forward direction omega m naught, and we have the no load speed in the reverse direction minus omega m naught. So, this is called the forward motoring. This is in the first quadrant, the quadrant 1, and this behavior of the motor is primarily called forward motoring, including all this. Now, this part of the behavior is called forward regenerative braking. So, this is in the second quadrant. So, this is the first quadrant, quadrant 1, this is quadrant 2, and we have the third quadrant and we have the fourth quadrant. So, in quadrant 2 we go for braking, that is the braking approach is the braking. So, this is forward regenerative braking, it means the energy is fed back to the supply. Here the power is negative in this case. Now, for the third quadrant here, this part is reverse motoring, including all this third quadrant part is the reverse motoring. Now, this is reverse regenerative braking. So, as we have got the forward regenerative braking, similarly we have reverse regenerative braking. So, it means in the negative direction we call this to be reverse, in the forward means the speed is in the forward direction we call forward braking or forward motoring, and in the reverse speed we call it to be reverse motoring or reverse braking. Now, the part of the characteristic which is appearing here. Now, if we go back to this equation is actually equation in the third and second quadrant. So, this is corresponding to plugging. So, when we have the no load speed is negative, we extend it to the second quadrant, we get plugging. So, this is plugging, but this part is called forward plugging. Forward plugging. This lies in the second quadrant, this is called forward plugging. It means the speed is positive, hence we call this to be forward plugging. This part of the characteristic for which the speed is negative, we call this to be reverse plugging. This is in the fourth quadrant. In the fourth quadrant again we have the braking behavior and this is the reverse plugging. Now, what about the dynamic braking? The dynamic braking, for that the applied voltage is 0. So, especially the speed torque characteristic lies like this. The no load speed is 0 here. So, this is the speed torque characteristic and this is primarily for dynamic braking. We call this to be forward dynamic braking. And this is called the reverse dynamic braking. So, when we have the speed torque characteristic of a separately excited DC motor both for forward and for reverse operation, we can identify forward motoring, forward regenerative braking, reverse motoring, reverse regenerative braking, forward plugging, reverse plugging and forward dynamic braking and reverse dynamic braking. So, this characteristic shows the complete behavior of separately excited DC motor. Now, let us try to see similarly that of a series motor. So, what we will be discussing right now is the motoring of a series DC motor and we also discuss about the braking of the DC motor. Now, for motoring we have already seen the circuit for the series motor. The field is in series with the armature. So, we apply the voltage here, the DC voltage, we have the back EMF E and the total resistance of the circuit is R is equal to R A plus R F. The current which is taken by the motor is I A Now, in this case we can write down this equation V is equal to E plus I A R, or E is equal to V minus I A R, or omega m is equal to V by under root k k f under root t minus r by k k f. So, here the torque equation is T is equal to k k f I a square, torque is proportional to the square of the current, and the back EMF E is equal to k phi omega m, that is equal to k k f I a into omega m. So, this is the motoring of a series motor. Similarly, we can go for the braking. In case of the braking here, what we do here is that we change the connection of the armature. So, what we do in this case, we change the connection of the armature with respect to the field winding. So, this is the applied voltage V, and here we have the back EMF E and the total resistance is R. So, if we write down the voltage equation, V is equal to minus E plus I A R, or we can write down the equation for the speed, E is equal to minus V plus I A R, or omega m is equal to minus V by k k f under root t plus r by k k f. Now, this is the equation for the braking. Now, this braking is a special type of braking, this is called plugging. In series motor, when we talk about braking, it is usually plugging. We reverse the armature connection, and the motor torque decreases. Here the torque is negative, because the torque here, because the connection has been reversed. So, the torque here is minus of k k f I a square, torque is negative. So, when the torque is negative, we call this to be braking. Now, if you see the characteristic, the speed torque characteristic of a series motor, we have speed in the y axis and torque in the x axis. This is how we plot the speed torque characteristic, and for the reverse motoring, this is our speed torque characteristic. So, this part is forward motoring, and this part is forward plugging. Similarly, this part here is reverse motoring, and the part which is in the fourth quadrant is reverse plugging. So, in series motor also we can go for motoring and braking. The motoring occurs in first quadrant and third quadrant, and the braking occurs in second quadrant and the fourth quadrant, and popular method of braking in series motor is called plugging. So, we stop here for today's lecture, we will continue in the next lecture.